We'll continue from where we left last time. So, recall we were looking at problems in network information theory, and as two important examples, we looked at the broadcast channel where there is one sender and two receivers. Sender wants to send messages M1 and M2. M1 is meant for receiver 1, M2 is meant for receiver 2. And we looked at a classical inner bound, a classical protocol for this problem given by Martin. And we went through Martin's classical proof, and then our aim is to try to transport this proof to the quantum scenario. So recall that the channel is a CQ channel, so the input is classical, output is quantum. And we saw that there was a problem in doing this, and that problem, like we call it pitfall, and so I'll recall what the pitfall was, and this is the span of subspace pitfall, whatever, related to, yesterday I called it the binning pitfall. So it's related to a technique used in classical information theory called binning, and what was the pitfall? So to exemplify it, let us say that there are, like, one is trying to build a code book using some random variable u1. Okay? In this setting, we take n IID copies, let us say. And there are a whole bunch of these samples that I take. So maybe 2 to the n R1 tilde of them. And there is a receiver who gets a state that depends upon what was transmitted. So let us say the first message was transmitted, and the sample corresponding to it is this quantity u1 n bracket 1, and the output state for that is given by rho. And the receiver wants to do a joint typicality kind of projection, but because of the idiosyncrasies of our protocol, I mean, if you're trying to do what Martin did, so instead of just treating these samples as it is, we partition them into bins, and each bin is of size 2 to the n R1 tilde minus R1. So the number of bins is 2 to the power n R1. Okay. And for some reason, which is not important today, but for some reason, I mean, that was explained yesterday for Martin's strategy. For some reason, the receiver gets the state, and the receiver wants to check whether whether this state is jointly typical with one particular bin. Okay, so let us say this is bin number M1, and question is so B1n, okay, whatever, jointly typical with bin number M1. And so we have to formalize this, and what was the classical way of formalizing it? Saying that it's jointly typical with respect to bin number M1 is formalized by saying that it is jointly typical with respect to at least one such sample in this bin. Maybe it's jointly typical with respect to many such U1 samples within the bin. That is fine. Okay. And Martin's strategy was we want the received state to be jointly typical with exactly one bin. Okay, or else there's an error. So classically, this was easy to analyze. I mean, so let us say message number 1 is sent. So message number 1 in bin number 1. Okay, so let us say message number 1 is sent in bin number 1. And what is the probability of the error? There is one source of error coming that, okay, the received state is not typical with bin number 1. It's not typical with any message out there. That's less than epsilon. In fact, we expect it to be typical with the very first message out here, the very first sample out here. Okay? And the second source of error is maybe the received state is jointly typical with bin number 2 or bin number 3 and all. Okay, so we did a union bound classically, and to say jointly to bin number 2, we further broke up that union bound into union with the samples in bin number 2, union samples in bin number 3, and that all that worked. Okay, but quantumly this was the pitfall. So how do I say it's jointly typical with a bin? The natural idea would be, okay, so now saying that it's jointly typical with respect to a sample U1 was like doing a projection onto a subspace. So but for a bin there are several subspaces corresponding to each possible sample out here. So jointly typical with respect to a bin, the first way of formalizing is take the span of the subspaces. Okay, but then there is a very fundamental geometric problem, recall. So suppose this is the quantum state and these are two subspaces to project onto. In fact, V1 is completely orthogonal to psi, V2 is almost orthogonal. So if it was classical, then I could have taken the union of this, and that's still small, 0 plus epsilon. Okay, but quantumly the span of this, I mean, is the entire plane of the board. So psi will have projection of length 1 there. So this was the problem. So how do you? So this was pitfall 1, and then there was another pitfall which I'll recall when we come to that. So how will you get past that? Okay. So we'll need a new lemma, which we'll call the quantum multi-hypothesis testing lemma. Okay. So there's some new jargon, hypothesis testing. It will become clear in a moment. So on the left-hand side, I mean, we are motivated by some network information theory problem. We've seen some pitfall, and the pitfall comes because of the span does not behave like the union. I mean, span seems like an analog of the union, but it does not behave like the union because of pictures like this. So we really need some new geometric result, and so I'll first state this result, and using it, we will see how to get past that pitfall. Okay, and later on, maybe at the end of today and tomorrow, I'll give an idea how to prove this hypothesis testing lemma. Okay, so what is this lemma? So I have, let us say, two sets of quantum states, rho 1, rho 2, rho k. This is set number 1. And set number 2 is sigma 1, sigma 2, sigma L. Okay? K and L have nothing to do with each other. Okay? And I'll call this positive instances, the positive hypothesis. I mean, the meaning will become clear in a moment why I'm calling this positive. And the sigmas I'll call the negative hypothesis. Okay. Now, if I take rho I here and sigma j, like choose a positive hypothesis, choose a negative hypothesis, ij. So there is a P of M element pi ij. So for every pair ij, there is a P of M element pi ij. So all I'm saying is that this is something less than the identity. Okay. So think of this P of M as a test to distinguish between positive and negative. What this test does is, it does very well on the positive instance. So trace of pi ij rho I is larger than 1 minus epsilon. Okay, and this test does very badly on the negative instance. Okay, so I mean, I'll not give a name to it. So this is small. Like, okay, typically, I mean, it's exponentially small in some other parameters of the problem. And when I look at concreteness, so it's like exponentially small. Okay, so. So for every pair of rho I and sigma j, there's a test which distinguishes between them. Okay, the test does very well on the rho, very bad on the sigma. Okay. Yeah. So of course, I mean, This is part of the hypothesis of the problem. So that's why I'm calling this positive instances, this negative. So the guarantee is not very severe. All I'm telling you is that the trace distance between rho I and sigma j is large. Okay, I mean that. I mean it's almost like that. Okay. Yeah. Okay. Yes. Okay. Yeah. So I'll save more of this. Yes. Yes. Of course. The catch here is this pi ij depends upon, I mean, what you are trying to distinguish. Okay. But I'll tell you what my aim is. Okay. So my so this is what is part of the setup. Like this is the input to the lemma. So there is a set of positive instances, set of negative instances, and I assume that for every pair, rho I sigma j, there is a test that distinguishes between them.
In case rho I is equal to sigma j for me.
Well, I mean, I never told you what this is. No, they will be the same. I mean, you will get some trivial statement as the conclusion of the lemma. Yeah. So it's only interesting when each rho I is well separated from sigma j. Okay.
We can assume the sets are disjoint.
Yeah. Assume the sets are disjoint. Or else, I mean, we'll get trivial statements. Yeah. So, I mean, for this hypothesis testing lemma to have any punch, I mean, we require that, I mean, each row is far from each sigma. Okay. So, two sets of states. But I'm not telling, I mean, okay, fine. I mean, I'm not told you what I'm about to do with them. Okay. So, so suppose I have a setup coming from somewhere for this. Okay. So, but I mean that's why I'm calling them the positive and negative hypothesis. I mean to really drill into you that that each row is well separated from each sigma. Okay, and by that I mean there's a test which distinguishes between rho I and sigma j. Okay.
Is this very similar to Bhattacharya bounders or something?
Yeah. If you just a one row one sigma, I mean the trace distance. Fidelity, I mean this is what you would get. It's not exactly equivalent because the problem is, let us say I just have one row and one sigma. So what I want is to find a pi that accepts rho with probability 1 minus epsilon, and then I want to make this as small as possible. Okay. So you can see what you get from the trace distance, but that's not the best POVM that would come out. So you actually have to solve a semi-different program if you really want to make this exponential small. There's a name. I mean, the people have studied this problem precisely when there's one row and one sigma. They even gave a name for it. It's called, in the case of one row one sigma. Okay, which is the epsilon here is. There should exist a POVM element which accepts rho with probability 1 minus epsilon, and then that POVM element should accept sigma with as low probability as possible. So this is minimum, whatever, maximum over lambda, such that and trace pi rho is larger than 1 minus epsilon. Trace pi sigma is less than 2 to the minus lambda. Okay, so this is the problem. So look at all POVM elements pi which accept rho with probability 1 minus epsilon. See what's the probability with which pi accepts sigma. Call that 2 to the minus lambda and try to minimize that. Okay. So this can be solved by doing some semi-definite programming. One can find out what the optimal lambda is, and that's that's what I'm talking about. So but now for every such pair, I mean there will be this quantity that you can compute. Yeah. Yeah. There's I think a name for this is by Wang and Renner and okay, but yeah. But I mean, this is just notation. So really what I want is a test. Okay. So, okay. So this is just the setup. Okay. So suppose, I mean, this is the setup. I have set of positive hypothesis, negative hypothesis, and I have for each pair, I have a distinguishing POVM with these features. I mean, it has to accept positive hypothesis with 1 minus epsilon, and it has to reject the negative hypothesis as much as possible. Okay. So for each such pair, one can solve a semi-definite program, find the pi ij. But now what I'm going to do, I want a single test that distinguishes between rho and sigma. Okay, so this is multi-hypothesis, a multiple positive hypothesis, multiple negative hypothesis. I want a single thing. So this is the thing.
So is single POV that distinguishes any pair?
Yes, that's what I want. I'm writing. Then there exists pi tilde, single POVM element, such that trace pi tilde rho I so statement is not so nice, but we'll go through it slowly. So fix some alpha, okay. Then there exists the pi tilde. Pi tilde depends upon this alpha also, okay. Okay. So, and special case, which is an important special case. Special case is there's only one row but many sigma. So there's k equal to 1. There's only one positive instance but many negative instances. Okay. Then we don't need this alpha. Then I can say that then I have this very beautiful looking statement that pi tilde does like as good as the, well, there's no ij here now, really. I mean, I is 1, okay? So it does within a factor of 2 of the best thing that you can do, okay? I've not told you what this function is, so this approximately looks like epsilon to the power 2 to the minus k of that order, okay? The best, they are solution program. So they're definitely tailor-made to rho I and sigma j. And the amazing thing is that one can find a pi tilde. Okay? So, yeah, so Shomshur asked a very nice question. I mean, he said something about convex hull, so I'm coming to that. Okay, so, so a related question is, can I find a pi tilde which, let's say, accepts a positive instance with probability close to 1, maybe greater than 90%, and accepts negative instance with very low probability, probability less than 10%. Okay. So basically, I want some threshold such that all positive instances are accepted above the threshold, all negative are accepted below the threshold. So this problem has been solved before. This is possible if and only if I take the convex hull of the rows, convex hull of the sigmas. Okay. So now these are sets. Look at a pair of points in the convex hull here, which are closest in trace distance. Okay. So, so find out what the trace distance is, and that tells you what's the threshold. Okay, how I can distinguish, how much I can distinguish between them. So that has been solved before, but that's not what I'm trying to do out here. Okay. So, so what I'm trying to, so let us say the convex hull argument gives you some other POV element pi hat. Pi hat does a decent job of distinguishing not just every row from every sigma, but everything in the convex hull here from everything in the convex hull here. Okay, but that's not what I want to do. I really want to. I mean, I really want to separate each. I mean, some finite sets. I want to separate these k rows from k sigmas by one such POV element pi tilde. Okay. Alpha is something that will bite you here. Okay, so alpha is a parameter that you have to fix. Okay, so let's see what is the difference from the convex hull thing slowly. So the thing is, it's easier to look at the case when k is equal to 1. There's only one positive instance, just one row, and there are many negative instances sigma. Let's look at that case. Okay, I want to separate row from all the sigmas by a single pi tilde. Okay, still the convex hull argument is there, but the point here is that this does not contradict this. I mean, you may say the convex hull of the sigmas maybe contains the rho. If that happens, then I mean that can happen. If that happens, there's no contradiction here because, like I told you, this function does 2 to the minus L. Sorry. 2 to the minus L, number of negative instances. Okay, so this function, I mean, decays with how many sigmas I put out here. So I mean, it's still a function of epsilon and L, but I mean, it's not very nice. So the case when the convex hull of the sigmas will encompass rho, I mean, that gets reflected out here also. Then there will be no such gap between them. So really, I mean, for this thing to have any punch, I mean, the setting is that pi ij does a really bad job on sigma j. Okay, that's why I mean I wanted to drive home the fact that it's exponentially small. But in the actual mathematical statement, I mean I'm not even telling you how small this is. Like it makes sense as written. Okay, and typically the way we'll use it is like L is a small quantity. I mean L will be constant in the parameters of the problem. Just I mean the constant number. Well, there will be constant number of negative instances. Let's say one positive instance and maybe like some 100 negative instances, something like that. That's what we are trying to do. Okay, so the epsilon raised to 2 to the minus L is still not bad, and the amazing thing is that this just does a factor of 2 out here.
So what you are saying is that if I take the convex hull of the first state and the convex hull of the second state, and if they are disjoint, then you can figure out a POVM which will distinguish these two in the sense that even they can distinguish the closest two elements.
I'm not saying anything about the closest. So the earlier theorem says how well you can distinguish the closest of the two elements. But I'm saying something even better.
No, I'm not talking about this.
Oh, yeah.
You can come up with a POVM.
Yes.
Which can figure out distinguish the closest two elements.
That's right, but that will not do so well.
Right. So this is much better than
This is much better than that. Yeah. I mean, so it will be one lecture required to prove that. The other one is like 2 lines. So, yeah. So I just wanted to say, I mean, before you jump and say convex hull, it's already done. I'm saying it's not quite the same thing out here. Okay. So first look at the special case: one positive instance, many negative instances. So I do well on the positive instance. I mean, instead of 1 minus epsilon, it's 1 minus some function of epsilon and L. Function of epsilon L. And on the negative instance, just a factor of 2 away. Okay? So this is already good enough to take care of the second pitfall I mentioned the last time. Okay? We'll see, I mean, in the classical setting, I mean, it's very easy to, prove these kind of results. We'll prove it in a few seconds. Okay, so k equal to 1 case I have this. If k is not equal to 1, then the statement is no longer so nice. Okay, so what happens out here is the number of positive instances starts biting me. So to make sense of this, let us look at how we would prove this classically. Okay, so the way I would prove this classically is, so pi ij is a test. Okay, I mean it's just a subset. I mean, these are probability distributions. These are some probability distribution. There's some underlying sample space somewhere. So these are just subsets of the sample space. Okay. So for distinguishing between rho I and sigma j, there is a certain subset pi ij that I'm going to look at. Okay. So now to form the pi tilde, what will I do? Okay. Again, let us say that there's one positive instance. So what I will do is I'll take the intersection of all the pi j's. Okay. So that is really, I mean, what one did for pitfall 2. Like when I had several typical sets, I just took the intersection. That I would say, like, take the intersection of the things. Okay. So this, so the intersection is something that is contained in each of the pi j's. So classically, I don't even have this factor of 2. So I'll take pi tilde to be the intersection, and I'll get this for free. What will I get out here? I'll get 1 minus k epsilon. Sorry, 1 minus L epsilon. Okay, I'm taking intersection of these L guys, and I'll get 1 minus L epsilon. So the dependence is even better, but that's okay, what I have. And now, suppose I have several positive instances, what I'll do is, I will construct a pi tilde for rho 1, pi tilde for rho 2, pi tilde for rho 3, and so on, take the union of those things. Okay, so it's a union of intersections. So, I'll distinguish rho 1 from all the sigmas by taking the intersection of pi 1 1, pi 1 2, pi 1 3. Take that intersection, call it pi tilde 1. Okay, then similarly there's pi tilde 2, pi tilde 3, take the union of all those things. Okay, so if I do that,
So these pi I1, pi I2, pi
yeah,
etc., they're operators.
they are operators here between 0 and 1.
No, not in the classical.
Yeah, classically they're just subsets of the sample space.
What do you mean by intersection of these operators?
No, I've not told you how to prove it. I'm giving you classical. I mean, before you, I mean, why should you even believe me? First, you should see that classically this is true. I mean, classically is very trivially true. I'm telling you how to prove it. Okay, quantumly it's hard. That's why there are pitfalls. No, so okay, so yeah, yeah. I mean, and it's the union in it's the span and the intersection pitfall. So I'm telling you how I'll tell you how to do it quantumly, and I mean we'll see how, I mean what are the problems and what more we have to do. Yeah, no, start off with the classical. Let's see if it makes sense. So, pi tilde 1 was the intersection of pi 1 1, pi 1 2, pi 1 3, and so on. And that doesn't even have a factor of 2 here, and that is 1 minus L epsilon out here. That is pi tilde 1. But now there are several rows, so I'll take the union of pi tilde 1, pi tilde 2, and all this, and call it my final pi tilde. That will still have 1 minus L epsilon out here. Okay, and here I'll get the sum. Okay, out there. So actually, maybe I should even put a factor of 2 out here for it to be quite right. Okay, so here I'll just get the sum. That is no overall square root. There is no alpha, classically. Okay, so now you can see. I mean, okay. So it's something like this, very true classically, very easy to prove. There's the intersection thing, that is pitfall 2. Then there's the union thing where I would take the span, that is pitfall 1. Okay, so these are precisely the two pitfalls we have to address, and we can address it by proving a result like this. Okay, so what we can prove in the quantum cases, okay, instead of 1 minus L epsilon, it looks a bit worse, like this, okay, and there is the factor of 2 that comes in. That's when k equal to 1, and when for general k it gets even worse, and so I would have ideally like just the sum out here, or maybe some factors, but no. There's another term that alpha that comes in out here. So ideally, I would like alpha to be close to 1. I mean, okay, right? I mean, I don't want this bound to be too large. But if alpha is close to 1, this starts looking trivial. Okay, so that's the trade-off. So I have to trade off by taking alpha small out here, but that comes and bites me out here. Another thing that bites me is the square root. Okay, but still, these are not bad enough. Okay, I mean, we can make do with this. What is important here is I have the sum of these probabilities, and there's an overall square root. If I had square root of individual quantities, then it would have been useless for my purposes. Okay. So any questions? I mean, this is almost the classical conclusion that one can get. Just union of intersection. So span of intersection, whatever it means. No, they're not related. You choose a.
Related to the distances between these states, because that's how they're coming, right?
Oh, no. Epsilon. No, the epsilon comes from here. Is this epsilon?
So even in the single case.
Huh?
Even in the single case, the parameter epsilon should characterize some.
No. So let me put it. You fix an epsilon and find me the best pi ij that accepts with probability 1 minus epsilon, and this you optimize. This is a semi-definite program. So this is the feasible set over which you are looking for solutions, and you're optimizing this objective function. So yeah, that's the viewpoint. Okay. So any questions about that? Okay. So classically, such a thing statement like this holds, and quantumly, also what we can prove is close enough to it that things will work. Okay. So we'll not prove this now. What we will do instead is we will use this hypothesis testing lemma and try to address the two pitfalls. So already this first pitfall is on the board. Okay. Let us see how it solves the binning problem. Okay, the span problem. Okay, so to do this, we will. So Martin. So the Martin thing and the interference channel were there to illustrate the two pitfalls. But today we don't need Martin. We don't need interference channel. So we stay to have this binning problem and. Let us say, so what do you really want to do? There is, let's consider a point-to-point channel, single sender, single receiver. The sender, the input to the channel is classical, output is quantum, CQ channel. And the sender does a random coding argument, like whatever, chooses samples from U1 N, okay? The receiver gets a quantum state. And we know traditionally, there's so many proofs of HSW that you can do some, look at the received state and try to find what it is typical with. But today we will do some coarse graining. I don't want to find what it is typical with. I have artificially divided the samples into bins. I want to find what bin it is typical with. Okay, I want to solve that. Okay, you will tell me why do I want to solve it? This is because of Martin. Okay, so I don't want to decode all the way up to the sample that was transmitted. I want to decode only up to the bin. So how we do it? So we'll adopt a binary search decoder. Okay, so it's a new style of decoding, binary search. Okay, so right. So let us say row. So this state is received. What the decoder does is that the decoder first asks whether the received state is jointly typical with the second half or not. Okay. So what do you mean by jointly typical with the second half? Recall, for a sample, there's a notion of being jointly typical. There was certain subspace I would try to project onto. Okay. Now, I'll just take the span of the subspaces corresponding to samples in the second half. Okay. And whatever, or more formally, I'll look at the states in the second half, and those are my positive instances out here, okay? And that gives me magically this pi tilde, okay? So the second half will correspond. The second half corresponds to the positive instances, okay? So. Is it jointly typical with respect to second half of samples? Okay. So I'll ask that, and if the answer is no, then I will. Then I believe that what has been sent lies from the first half, and I'll refine. I'll do binary search, and after that, whatever, binary search. Okay. ... You can take it all the way down to get what sample you want, but since we don't want to do it, we'll just keep doing binary search till we hit the correct bin, and we'll stop there. That's how we'll decode it up to the bin. So this is the decoding algorithm. Let's analyze it. Is it clear? What's the decoding algorithm? Okay.
It will change the state.
Hmm?
It will change the state. If you want to
Yes. Of course. So you have to analyze that also. Okay. So let us see. So really, the two extreme cases that you have to do, and everything else will be, the error bound proof. Okay. so if you look at the analysis, really, I mean, we have to do two extreme cases, and everything else will be somewhere in between. I mean, in terms of the calculation, the two extreme cases are like either I'm from the first bin or I'm from the last bin. Okay. So let us first say that the received state comes from the first bin, and we'll analyze this decoding algorithm, and we'll see. I mean, what is the error probability? Okay. So suppose first sample from first bin is actually transmitted. Okay. So then the probability of correctly decoding the bin. Okay. So that will be okay. So let us say whatever. Okay. So suppose a sample from the first bin is sent, and just to drive home the point that whatever, it could be any sample from the first bin, I'll say it's message number 3 that still lies in bin number 1. The sample number 3 that lies in bin number that has been sent. So this is the received state row. Okay, and the probability of correctly decoding means that every time I do the test, is it jointly typical with respect to the second half of the samples? Every time that fails. Okay. So is it jointly typical with the second half? No. I do that, and finally, I mean, the binary search tree, I'm always moving left, and I land up at bin 1. So that would be the probability of correctly decoding. Okay. So I'll call it pi, I mean, whatever, second half, and this fails. So the hat here denotes, hat of pi means identity minus pi. So pi of second half means it's the span of the typical spaces for the second half, really. Okay, so project onto the second half. So I want that to fail. So that is pi hat, and whatever. I mean, this is a different second because now I have reduced my search space, and so on. Okay, so like every time I'm trying to project onto the second half, it fails, and this is the probability of correctly decoding the bin. So this is this expression exactly, trace of this. Yeah.
So almost like trying to infer from which bin the sample is.
Yeah, that's what I'm trying to do. And if it was really the point-to-point channel, I mean, I could go all the way and even get the sample, but I don't want to do that. I mean, because, as I said, I only want to go up to the bin level because, I mean, yesterday's lecture, I mean, in Martin's case, that's all that, that's what I really want to do. Okay. So we do this. So this expression, so this can be upper bounded by something which looks like this. So this is the non-commutative union bound. Okay. So we will tell you why, I mean, it's got a name. This is my bound.
You want the lower bound?
Yeah, lower bound, sorry. Yeah, you're right. So 1 minus this, sorry. Yeah, so it's 1 minus this, sorry. Okay. Again, I mean, this pi second and this pi second are different because I'm reducing the size of my search space, but few such terms like this. Okay. So let's see, again, classically, to make sense of an expression like this. So probability of correctly decoding the bin, suppose it's classical again. I mean, these projectors are nothing but sets. I want not to lie in the second half, not to lie in the second half, so on. Okay, and that will be lower bounded by 1 minus the probability that, like, I do lie in the second half somewhere on the way. Okay, and that I'll use the union bound. So this is the sum of the probabilities of lying in the second half on the way. So this is what I have. So classically I would get 1 minus, there is no 2 here and no square root here, this expression. So that would be the classical union bound. Okay. In quantum things are not so good. I get this factor of 2 and I get an overall square root. What is important here is that, okay, so it's an overall square root. So there is still a sum of these probability terms. Okay. Naive arguments would put the square root inside out here, like I'll get a sum of square roots, and that would be a killer. Okay. And there is an important point out here. So one can try to prove this result by using gentle measurement result of Andreas, but if you try to do that, we'll get a sum of square roots. Okay. And so this one is more powerful, but there's something beautiful happening there. So if you see how much the state is being perturbed, so gentle measurement result tells us more. It says that, okay, here is the probability of success. It's close to 1. So after the measurement is done, there is a little bit of perturbation, but because the probability is close to 1, the perturbation is small. How much is small? If the probability of failure is epsilon, the perturbation grows as square root of epsilon, okay, in trace distance. So actually, the states are being perturbed each time. They are moving away from, they are moving away from the ideal thing at the rate of square root of the probabilities. Okay. So and that is optimal. You cannot beat that. Okay. But nevertheless, if you look at what is the overall probability, I don't care how much the states are really moving as long as this probability is good enough. So the success probability does not decay so fast. Okay, if of this measurement. So they're two slightly different things. The actual state geometrically is moving away faster, but the success probability doesn't decay so fast. Okay, and that is the difference between gentle measurement and the non-commutative union bound, and that's captured out here. Okay, so we can do this, and now, any questions? Questions about this one? Okay, and now let us analyze what it looks like. Okay, so now how am I going to evaluate this probability? So remember, like I'm doing a random coding argument, so I'll take an expectation over code books, and then I can move the expectation inside the square root because of some concavity or something like that, and I can do all that. So I can whatever like do things like that, and finally we can get and this becomes the average. This becomes the average state out here because I'm taking expectation of code book. So always, I mean, this is the probability of projecting on the second half. Okay, so that's the wrong side. That's not bin number 1. So I always get the average thing out here. So trace probability pi second average, sum of such terms. Okay, I get this, and now I will apply the multi-hypothesis testing lemma. So to bound the first quantity, I mean, what do I really mean out here? So what is this pi second? So the pi second is this second half right at the beginning. Okay. So let's say if there are 1 million messages, this is from 500,000 to 1 million. Okay. So that is the second. So that's pi second, and this is the average state. So this average state will play the role of the negative instance. That will be sigma out here. Okay. And this is the case where there's 1 sigma, but there are many positive instances. So the positive instances will be rho 500,000, rho 500,000 plus 1 up to rho 1 million. Okay, so these are the positive instances of this lemma that I'm going to apply it in that setting. And then I get a pi tilde promised by the lemma, that is this pi second. For the next term, this is maybe from 2.5 lakhs to 5 lakhs. Okay, that is this second half out here. Okay, in that case, I will apply the hypothesis testing lemma. The positive instances will be rho 2.5 lakh, rho 2.5 lakh plus 1 up to rho 5 lakhs. Okay, the negative instance sigma is still rho bar. That gives me another pi tilde. That is this pi second out here. So this is how I'm going to apply this. Yeah.
Explain one more time what is rho average.
Oh, rho average is average of this when I'm averaging over the U1 distribution. Okay, and this I get because I do the random coding argument, I average over code books. And the thing is, the support of pi second, I mean the states that come here and, and this state, they are independent because, I mean, pi second is here and what is being sent is here. So they're independent, so I can do independent averaging. So I don't care to do averaging out here, okay? But I care to do averaging out here, and I can move that averaging operation of code book into the square root because of concavity. Okay? I mean, this is a standard argument in information theory. And doing that, I'm averaging over this row UN3, okay, over the choice of code book generation, and that gives me rho bar, which is, I mean,
It's essentially an average over coding.
yeah, it's an average over coding, correct. Okay, so that is this rho bar. Pi second, I keep it as it is out here. I mean, I'm not. If required, I could have even done an averaging out here, but I don't need that. Okay, and then to analyze it, like I have to tell you very formally what is pi second, and that comes from this hypothesis testing lemma. Okay, so okay, any questions? Yeah.
Can you please repeat the difference between the two terms because they look the same to me?
Well, so they're not the same. So remember, this was the binary search decoder. Okay. So I ask, is it the second half here? So that will be from 500,000 to 1 million. Okay. The next pi second will be from 250,000 to 500,000, and so on. So that's what these things are. Okay. Whereas this, I mean, this row UN3 is, I mean, yeah, I mean, row UN3 is the leftmost bin out here. Okay, so that is never in the support of this thing. So that's why on average this becomes rho bar. I have this, and to say precisely what is pi second for the first instance, I have to take positive instance row 500,000, row 500,001, all the way up to row 1 million. They are the positive instances. The negative instance is rho bar. For the next pi second, so it will be the positive instance row 250,000, row 250,000 plus 1, row 500,000. This is rho bar. This is what I'm going to apply. Okay, so I can do this. Okay, and let us see. So let us see what this comes down to. Greater than. So now, I mean, like we'll have to recall something from the HSW theorem. I mean, how these parameters look like. So, yeah. So how will this behave? So that comes from out here. I mean, so rho bar, recall, was the negative instance. So the probability of succeeding on negative instance looks like the sum of the individual negative probabilities. I mean, classically, recall there was no alpha, there was no square root. It was just these things. Okay, but now, I mean, we'll have the square root. So I'll get something like, so if I'm talking of the rate n r1 tilde, so this is something like 2 to the n r1 tilde minus 1 times 2 to the minus n, the mutual information. Something like this. Sorry, plus delta. Sorry, no, this is minus delta. Well, forget the delta. So this is the first term, and then there is this alpha here, and there is a square root up here. Okay. The second term will look like 2 to the n r1 tilde minus 2. 2 to the minus n I, and so this is how things will go. So in the usual way of doing things, like if I choose the rate r1 tilde to be slightly less than the mutual information, I would say that this is very small. Okay, so if I do that, what I would get something like, what else, square root. This looks like minus 2 to the n delta, I mean if it is the mutual information minus delta, so something like this. There is this alpha hanging on the square root here. This thing is a little bit less, but let me use the same expression out here, and so on. Sum of some terms like this. Okay. This doesn't look so good. I mean, this exponential is small, but there's a square root now eating on it, and there are several of these. I mean, one has to be a little careful. So, the question: how many such terms are out there? That is the depth of the binary search tree. That is NR. Okay, so I can say that this is 1 minus 2, 2 to the minus n delta by alpha square root, and this is NR. Okay, so these are the number of terms. That's the depth of the binary search tree. Okay, and whatever R1 to be out here. And now, okay, that's a breather because this is exponentially small in n. This is polynomial large in n. This will still go to 0. R1 tilde is whatever, is mutual information, it's constant. So this takes care of the scenario 1 when it's the leftmost bin. Okay, any questions? Yeah. So it's not the usual kind of calculation. Yeah. So I mean, we do make crucial is the fact that the depth of this binary search tree, I mean the number of these pi seconds that we apply is logarithmic in the total number of samples. So it's nr1. So we use this. Okay. So this goes to 0. Okay. If not, now we will. Okay. If not. Any question? If, now we'll look at the second scenario where what is sent is the last bin out here. Okay, and we'll see what the calculation looks like for that.
Is it going to be very different? Or
Is very different.
but this time you can expect just you go to the left hand side. So
Yeah. Well, yeah. Okay. So I will say this is the last bin, maybe last message, last bin. Okay. So now the probability of correctly decoding is every time I line second half, second half, second half. So it's okay. No hats here, pi second. Okay. So that's the difference. So if I apply non-commutative union bound, the hat will come out here. Okay, that's the rule. So nothing very different, but oh sorry, this. Okay, so I get this. Okay, so this will be un 2 to the n r1 tilde, un 2 to the n r1 tilde. Okay. And now you see, I mean, this I cannot average out to make it rho bar. I mean, because like. It's the last bin. It always lies in the second half. Okay, I mean this is. I mean, so what is sorry pi hat out here? Okay, I mean this was pi second, so this is pi hat second. Okay, so this is the other kind of thing that under normal circumstances under normal circumstances this would be what? This is. I mean, I'm sending something from the last bin, and I'm seeing whether I'm typical with respect to second half. Of course, the probability should be close to 1. I mean, it should like 1 minus epsilon. So this one is 1 minus 2. So all I can say is epsilon out here. Whatever this ff. The epsilon that comes up from out here, but where here L is anyway. I mean. So, like here there was only one negative instance. So, I mean that is square root epsilon or something, doesn't matter. And yeah, alpha is something set small. So let me just call it something, it looks like square root epsilon, but this is really scary. Square root epsilon here, square root epsilon here, square root epsilon here. How many such terms? Again nr1 tilde. Okay, depth of the tree, that is nr1. So now I'll use the fact that what is the dependence of n and epsilon. So remember, like in the IID case, if I want an error epsilon for the typical projector, okay, I can set the number of copies. The point is, the dependence between n and epsilon is n grows like log of 1 over epsilon. Okay, so I mean, this follows from chain of bounds or something. So n behaves like log of 1 over epsilon. So if I put that in, this will also, whatever, like, I mean, the probability of success will go to 1 out here. So it's a very different calculation.
But here, why you can't do that body of the left half?
No, why cannot? I'm not saying that the left half projector plus the right half projector is the identity. That's not true.
No, like in the earlier calculation.
Huh?
In the earlier calculation, I mean, like when you send the first guy, and then you were asking the question that what is the
No, I have to specify my decoding algorithm. My decoding algorithm is it jointly typical with respect to second half? Answer is yes or no. Okay, but saying that something is not jointly typical with respect to second half doesn't mean it is jointly typical with respect to first half. I mean, I'm not, so whatever, this corresponds to some projection pi tilde coming in. That will correspond to some other projection. I have to now take my positive instances to go from row 1 to row 500,000. Okay, that's another pi tilde. There is no reason why these two pi tilde should add up to identity. Okay, so you're either jointly typical with respect to the second half or not. But if you're not, that does not mean you're jointly typical with respect to first half with certainty. Okay.
Actually, that's an important one. So can you say it again? What you choose then is the negative hypothesis? What's the state?
Rho bar. Always rho bar. Always rho bar. Always rho bar.
So it's like a null, basically.
Yeah. So I mean, I have to define my algorithm, right? So I have to fix at the beginning of the decoding what is pi second, and that's always chosen coming from here. Fix this to be rho bar. The first pi second is rho 500,000 to rho 1 million. The second one will be rho 250,000 to rho 500,000. Okay, so that's how pi second is, and the analysis now looks different because the probability of success is pi second always succeeds. The non-commutative union bound will analyze it by saying pi second fails. Okay, but the probability of pi second failing is not so small. It's epsilon or whatever, maybe even more precisely square root of epsilon out here. Okay, so and that's really scary. The square root of epsilon getting added a few times, but it's only a few times. It's nr1, and n only grows like log of 1 over epsilon. So it's very important that, I mean, in the IID case, we use the n coming from Chernoff bound. I mean, there are information theory texts where they use Chebyshev bound, and then n will grow only polynomially in 1 over epsilon, and then you're gone. Okay, so we have to use the best technology for IID, that is Chernoff bounds. N grows like log of 1 over epsilon. Put this out here, and then we can handle this. Okay, so any questions about it? And every other case, I mean, if you have some intermediate cases, then it will be a combination of these two calculations and whatever. We know how to control both of them now. So any questions? So this is how I'm going to handle probability of decoding a bin. Take care of pitfall 1. Okay, if no questions, I'll go to pitfall 2 and we'll see how to handle it, again using multi-hypothesis testing lemma. So this is the intersection of subspaces. Pitfall, let's call it. We'll recall what the pitfall is. What was the classical approach? I mean, that was intersection of sets. My whatever perverse nature, I'll say second half. But you fix it once and for all before, and this I mean, you can do this analysis. Okay, so Just to make things clear, I'm saying that there are two kinds of calculations that come in, and we can handle both of them by different arguments. Okay. The point is we need a binary search decoder. So this is something new. So people either did the pretty good measurement, Hayashi Nagaoka, bam, you get that. Okay, that's not going to work. There was sequential measurement where you actually project on the typical space one after the other, and you can analyze that also by the non-commutative union mount. We cannot even do that. We have to do binary search measurement.
Why is it necessary?
Oh, it's necessary because we have to handle this span, you know. And I mean, if this square root wasn't there out here, then I could have just done plain sequential decoding. But this square root is here, overall square root. Okay. I mean, if the square root was inside there, then it would be hopeless. I mean, I would not be talking today. Okay. So this square root is there, which makes things bad. But the point is the depth of the binary search tree is not so bad. It can handle this square root.
You can apply the
Yeah, I mean, the multi-hypothesis thing comes with an overall square root. But when I say the second half, so all the samples in the second half, they will be inside. They will get added up. Okay, but then there are several second halves to consider. No, the 500,000 to 1 million, 250,000 to 500. So there are several of them. So I'm going to do a sequence of this. I mean, I'm going to apply this multi-hypothesis lemma several times, and each time there is a square root out here. So several such things will add up, and I mean, whenever square roots add up, that's a reason for concern. But the point is, it's the depth of this binary. I mean, yeah, the number of iterations of a decoding algorithm cannot be too large. Okay, so that's why we needed the binary search tree. Okay. So pitfall 2, and we'll try to recall what the pitfall 2 was, and that was illustrated by the two sender multiple access channel. There are two senders and one receiver, and sender 1 wants to sender 1 wants to send M1, sender 2 wants to send M2. M1 is encoded into IID sequence over X, M2 is encoded into IID sequence over Y. What comes out here is, okay, and this I want to decode, and the receiver wants to know both M1 and M2. This was the problem. Classical quantum channel, input is classical, output is quantum. Okay, and we'll see what the classical way of doing this was. Okay, and I mean that involved taking an intersection of sets, and that's why I mean analogous thing we'll have to take intersection of subspaces, and that's the pitfall. Okay, so so I'll tell you what was the decoding strategy. Okay, so before that one step. Okay, so again, I mean, I want to construct a random code book. So M1 ranges from 1 to 2 to the nr1. M2 ranges from 1 to 2 to the nr2. Okay, and so this is xn M1. These code books are chosen by taking independent samples, and this is what comes out. So xn M1, yn M2. This is what comes out. Okay, and decoding strategy. Again, we can take a plain sequential decoding strategy. Okay. Check. So the receiver, let's say, receives some state. Okay. Okay. M1, M2 unknown. So check if received state typical with respect to xn1, yn1. Okay. So then check whether it's typical with respect to xn1, yn2, whatever. So take some lexicographic ordering, let's say on m1 and m2. run through them in sequence, and then check whether typical with respect to just one after the other. So of course states get perturbed, but we have our union bound out there. So then check typical with respect to xn1, yn2, and so on. Okay, lexicographic order, if you want. Well, order doesn't matter. This is the decoding strategy. So now, if you have to analyze it, so let us, so the worst case, let's say, comes out to be that, that what is sent, the M1, M2 that is sent is the very last thing in the lexicographic order. Like M1 is 2 to the NR1, M2 is 2 to the NR2. Okay? So then the probability of correctly decoding will be rho and then I will take pi xn1, yn1. Sorry, it has to fail for that. I mean, if you see it's typical, some in the way you will stop and declare that to be my guess. So I have to go till the end, so it has to fail. So it is pi hat xn1, yn1. Then I'll have pi hat xn2, yn2. Sorry, xn1, yn2, lexicographic order, and so on. So this is my success probability. I'll apply the non-commutative union bound. So it's larger than this. And then, so there'll be one term which will look like trace of, so at the very end, this is a pi. When it becomes, finally I want to succeed on xn 2 to the nr1, yn 2 to the nr2. So all these are pi hats. I have to fail at all the earlier steps. At the very last step, I want to succeed because so then there is this pi xn 2 to the nr1, 2 to the nr2. Okay. So apply the non-commutative union bound. So this I will get trace of pi hat xn 2 to the nr1, yn 2 to the nr2. And the others will be all pi's, right? Okay, pi hat is pi. So I will write whatever a b whatever a not equal to 2 to the nr1 or b not equal to 2 to the nr2. Trace of pi xn a yn b, and this is rho xn, oh sorry, the same thing, rho xn r1 okay. So this is how the expression looks like. So this is the thing that, okay, I mean, under normal circumstances, rho should be typical with respect to the, I mean, the correct typical projector. I mean, 2 to the nr1, 2 to the nr2. So this should succeed with probability 1 minus epsilon. So pi hat says that it fails, so that is at most epsilon. So this gives me epsilon. The other one will give me those exponentially small entropic terms. Okay, I mean, hopefully. So let's see what happens. So there are 3 kinds of terms that appear in this summation. So what I know is that the pair a comma b is not equal to 2 to the nr1, 2 to the nr2. So I know either a is not equal to 2 to the nr1 or b is not equal to 2 to the nr2 or both. Okay. So there will be something that looks like, so I'll just write 3 terms, 2 to the nr1, yn b. So there will be one such summation over these things. Okay. Then there will be another thing, summation over and then there is, so this is, I mean, both A and B are different from 2 to the NR1, 2 to the NR2. Okay, so overall square root. So the 3 types of terms come out here. Now I'm doing random coding arguments, so I take an expectation over the codebook generation. I move the expectation inside the square root sign as before. That comes in out here, and let us see what would get. So if I apply the expectation over this term, I can only, I mean, this yn b and yn 2 to the nr2 are independent. Okay, b is not 2 to the nr2, so they are independent. So I can take the expectation here independently of this. So there's something like this. So yeah, so how many such b's out there? Like for message 1, it's the same coordinate, that's fixed. How many such b's out here? So that's 2 to the nr2, and just look at one such term. By this term, I mean I've averaged over the y. So there is a certain kind of averaging out here. Okay, so maybe to emphasize that, I'll put rho bar out here. But I fixed the x part, I'm only averaging over y's. There is a similar term here where I'm averaging over the x's, so it's rho bar yn 2 to the nr2. Okay, and there's a third one where, I mean, both a and b were different, so that is at most this number of this, and this is trace of, and this is rho bar. I've averaged over both x's and y's. So these are the 3 kinds of terms that appear out here. Okay, and now ideally I would like to say that this trace is less than 2 to the minus n mutual information between b and y given x. This is what we manage classically. This I would like to say it's less than 2 to the minus n ib and x given y. I mean, what is given out here, what it is conditioned on is like this coordinate. Okay, and this will be less than 2 to the minus n mutual information of b with xy, no conditioning out here. So classically this is what happens, and I would like to get the same thing quantumly, and so let us see how the classical argument went. Okay, any questions about this? So I mean, we are going to analyze these 3 terms and see, I mean, where they came from classical and where the pitfall is, and that is the intersection of subspaces problem. No? So I'll wipe out this part of the board. We just need these 3 calculation terms. Okay? Okay. So classically, there are 4 kinds of typical projectors that came out from just, I mean, IID theory. So this is typical. So what are the 4 kinds of states that we are dealing around with? Rho x and yn, I mean, whatever. X and yn are fed here, and this is the output state, that is rho x and yn. Then remember, like sometimes I need to, out here I need to average the y's out. So there is rho bar xn. Sometimes I need to average the y's out, that is, sorry, average the x out here, so this. And sometimes I need to average everything out, that is rho bar. So these are the 4 types of states under consideration. And each one of them comes with typical projector in a natural way. Okay, and what is the property? So one property is trace of pi xn yn. I mean, one property that will be equal is greater than 1 minus epsilon. And the other properties are trace of pi, sorry, not this, sorry, pi xn, rho xn, pi xn. Okay. So, I mean, this operator has very small eigenvalues. So this is, sorry, entropic quantity. This was there. One more thing. The rank of this typical projector pi x n y n is not too large. So these are the inequalities that, I mean, we use in the standard argument. Same thing holds classically, same thing holds quantumly. Okay. So far so good. And from here I want to be able to get these mutual information type of quantities. So I will do some calculation. So the first one, epsilon here comes from this thing. Okay.
The last inequality is just less than or equal, not very much less than, is it?
This one you mean? Well, you have to put a plus delta out here. Okay. So the point is that this is, I mean, tied both ways. So there are corresponding lower bounds also. Okay. So to really get the upper bound, you have to put some maybe minus delta here and lower bound plus delta. I mean, okay. So, but we'll use these directions, but the other things also hold. And it turns out you can, I mean, at the end of the day, take it to that multi-hypothesis testing setting also. So, yeah. So there are other problems in information theory where we'll use the lower bound parts. And we have analogs for them in the multi-hypothesis testing thing also. Yeah, so you can even say approximately equal to this thing. Okay, so this epsilon came from here. Let us try to see where, let's look at this term, okay, which corresponds to this. So let us see, okay, so let us see where where this mutual information term comes from. Okay, so okay, what do we do? So as I told you, like, check if receive state is typical. Now, so I have to tell you what projections or what tests, okay, the decoder is typically doing. So first, let's see what the classical decoder did. So I mean, these were typical sets. These were subsets of the sample space. Okay, there are 4 kinds of such typical sets. The classical decoder took the intersection of them. Okay, and that was the like. What we will say, pi tilde x and yn is defined to be intersection of pi x and yn, pi xn. Okay. So this is the classical prescription. Take intersection of these things. Okay. And now let us see. Okay, so first thing to check is this still epsilon, because now pi tilde is smaller than pi, but you don't lose much in that intersection. You can prove that classically, and so I mean that epsilon is still there. I'll not get into that. More interesting are these terms, where they come from. So, okay, so if I look at trace of pi tilde xn yn, rho bar xn, I want to upper bound this. So, so remember, pi tilde is So at least classically I can say this. I mean, it was the intersection of all these sets. So definitely it's contained in the intersection of two of them, namely pi xn yn and pi xn. So let me write in this fancy operator theoretic way, but it's nothing but the intersection really. Okay. So I can write this. And now this is less than like the rank of pi xn yn. Okay. And whatever cyclicity of trace, it's less than whatever the L infinity norm of pi xn rho bar xn. I mean the largest eigenvalue of this. Okay. So for which we have this expression out here. So trace of pi xn yn is less than 2 to the n times h of b given xy. And the L infinity norm, the largest eigenvalue, whatever, classically the largest probability restricted to that event, I mean the largest probability of a point in that event is upper bounded by this. So this is 2 to the minus n h of b given x. And this is exactly the mutual information term that I am shooting for. That's where this came from. Similar analysis for this one, I'll again use the intersection projector, but now I will put cheekily put a yn out here. Okay, and this was rho bar yn. Repeat the same thing, get this information term. Then for the third one, I have a rho bar out here. Then I'll cheekily put a pi out here. Pi xn is still there. Okay, do the same thing, and I'll get the correct entropic term out here and the correct mutual information term out there. So this is the classical proof. Okay, intersection works beautifully. Okay, but what do we now do quantumly? I mean, intersection of subspaces, that's probably the zero subspace out here. Okay, so we will make use of the multi-hypothesis testing lemma. So 2 minutes should be done. Okay, so what we will do is, so I have to tell you what the positive instance are. I'll now take one positive instance, that is rho xn yn. And I'll take 3 negative instances, rho bar xn, rho bar yn, and rho bar out here. Okay, apply the lemma. So the lemma gives me a pi tilde, okay, coming out here, and that's the pi tilde that I will use. So what does this pi tilde do? It will accept rho xn yn, the positive instance, with probability 1 minus maybe the 8th root of epsilon or something like that. Okay, so fine. Maybe this looks like 1/8, not too bad. Then for the negative instances, okay. So what is pi j out here? Pi j is yeah. So I have to. I told you what the positive instance are, negative instance. I actually also have to tell you what the pi j's are to separate the positive instance from each negative instance. So the pi j's, okay. So the pi j's morally are the product of pi xn yn, and so yeah, actually, not more like I can tell you. So what is so what is the separation between rho xn yn and rho xn? What is the separating POVM element? That is precisely this. Okay. For to separate rho xn yn from rho bar yn, what is the separating POVM element? That is this thing with the yn. Okay. And to separate rho xn yn from rho bar, the third separating POVM, that is this expression with pi around it. Okay. So 3 different POVMs, separate them. I mean, these are the dream POVMs. Okay. And the hypothesis testing lemma combines all of them into pi tilde, which gives you 1 minus 8th root of epsilon, not too bad. And the performance on pi tilde is as good as the dream POVM with a factor of 2. So the same analysis goes through, and I get the mutual information. Okay. So this is the analog of intersection of spaces. So recall when you took union of spaces, there were several positive instances, 1 negative instance, pitfall 1. To address pitfall 2, to do the intersection, there was 1 positive instance, several negative instances. In general, of course, both the pitfalls come in together. So there will be several positive instances, several negative instances, no problem. Okay, so there is, in fact, so as I said, there is a simple Martin inner bound, I said last time, which illustrates pitfall 1, but there is a more complicated Martin inner bound. It's called Martin inner bound with common message. So that's the best result known classically for the broadcast channel. That's a case where both the pitfalls will come in. Okay, and then but then we have the technology ready for that. Okay, any questions?
Now my mind is very clear as to what the sequence I relax this afternoon. 2:30 we will have the tutorial by both Eric and Pranab. And 4:30 we will have Eric's lecture continued. And no limit, you can go as long as you have energy and ammunition. And depending on that, we can have the discussion. Probably, I think we should think that we should have the discussion immediately after that 6 o'clock break. 6 to 6:30 there will be a break. At 6:30 we can meet briefly.
I probably wouldn't go an hour or so. I mean, unless
Okay,
there's
we'll
questions,
see.
so,
I mean, we will keep it. So I don't want it to be a pressure on you.
yeah, no, it's
So we will keep both options open. But these two are very clear. 2:30 tutorials, 4:30 Eric's lecture.